Let's do a problem. So here's the statement. So let's take the field Fp. This is the finite field with P being a prime. Okay, and consider the following polynomial. Let's take f of x to be the polynomial x power p minus x plus a constant a, where a is an element of Fp, but we assume a is not 0. Okay, so the question says prove that f is an irreducible separable polynomial. If it's an irreducible separable polynomial in Fp of x. Okay, so let's prove this. So here's the solution. It involves lots of little things that we have learnt along the way. So it's a nice application of many of the facts we've seen. So let's go ahead and do this. So first, let's check separability. So why is f separable? Recall the criterion for separability, which says that if the GCD of f and f prime is 1, then f is automatically separable. Okay, so now in this case we just have to compute the derivative. So let me call this df of x or f prime of x. So the derivative, which is in this case just px to the p minus 1 minus 1. But remember, we are over Fp, and so p times anything is just 0. So that first term vanishes. So this is just the polynomial minus 1. Okay, so obviously the GCD of this polynomial df or f prime with the original polynomial f is clearly 1. Okay, so this means then, so this is true, and so of course this means that f is separable. So here I've used the criterion for separability in terms of the derivative. But there's another way of doing this, which is, so recall we are asked to show two things. One, that it is irreducible as well as separable. And so recall, so another way, maybe another approach is the following. Recall that Fp is a perfect field. Okay, and recall that meant that what we call the Frobenius automorphism, the map which sends every element to the pth power, is an isomorphism of this field. Okay, so this is a perfect field. Therefore, what does that mean? Any irreducible polynomial is automatically separable. So this was what perfectness allowed us to conclude. This implies every irreducible polynomial in Fp of x is automatically separable. So I have used that result that we proved about perfect fields, and so what does it mean in this in the context of this problem? Therefore, it's enough to prove that f is irreducible. So we were asked to prove both. So it's enough to show just one thing, that f is irreducible. That would automatically imply separability. So let's show that f is irreducible. So observe that if a is 0, so remember our assumption was that a is not 0, but let's just pause for a moment and wonder what happens if a is 0. Then the polynomial is just x to the p minus x. Okay, and this is of course not irreducible. You can pull out a common factor of x definitely, but in fact you can exactly say how this factorizes. Observe that if I take any element alpha in Fp, the finite field, then alpha power p is exactly alpha, right? So you have seen this in the construction of finite fields. So what does this mean? This means that every element alpha of Fp is a root of this polynomial, and so we can write this polynomial. It factorizes completely, it splits completely over Fp as follows. Okay, so it's just a product of x minus alpha as alpha ranges over Fp. Okay, good. So we know that A is not 0 is definitely required. Okay, so we have, however, that A is not 0. Okay, so now let's write out our polynomial. So this looks like x to the p minus x, and there's an additional factor of A. Now let's do the following. Since A is not 0, I'll pull a common factor of A from everything. Write this as A inverse x to the p minus A inverse x plus 1. So my goal is to get the constant term to be a 1 here. Now this is, well, I can rewrite this as A times y to the p minus y plus 1. So I'm changing variable here. Y is just A inverse x. Okay, and why is that? Why is the first term y power p? Observe that we've just said that here, that every element of the base field fp, its pth power gives you alpha. Okay, so y is A inverse x means that if I raise this to the pth power, it's going to give me A inverse to the pth power x to the pth power, but A inverse to the p is just the same as A inverse, because A inverse is an element of my field fp. Okay, so okay, good. So what does this mean? It basically means that I can rewrite this polynomial in such a way that my constant term is a 1. Okay, so let's write that out here. So g of x equals x to the p minus x plus a 1. So observe, so I'm going to define g in this way, so let g be defined in this manner. Then observe that f and g are more or less the same polynomial, they just differ by this following very simple transformation. I can change variable to A inverse x and I pull out a common factor of A. Okay, so f of x is just a polynomial A times g of A inverse x, or equivalently I can change x to ax and write this as g of x is nothing but A inverse f of ax. Okay, so what's all this in aid of? Well, in particular, this means the following. This says that if f, so maybe I'll number the facts along the way. So let's see, this is if A equals 0, what happens? Step 2 is this simplification here. Step 3 is realizing that, well, okay, maybe this is still step 2. So observe that if fx is irreducible, then so is gx. So observe f of x is an irreducible polynomial. So observe this is also a polynomial with coefficients in fp of x. So f of x is irreducible if and only if g of x is reducible. Okay, how do we prove this? Well, it's easy enough. So let's suppose g is reducible. So here's a little proof of this fact. If g can be written as a product of two polynomials, say let me call them m of x and n of x, both polynomials with coefficients in fp, then just use this transformation property. How do you get f from g? Well, f of x is just a times g of A inverse x. So it's m of A inverse x, n of A inverse x. Okay, now observe that this gives me a way of writing f as a product of two polynomials, because, well, these are also polynomials with coefficients in fp. Okay, so let me assume that m and n with let's say degree of m and degree of n, and they're both polynomials of degree strictly smaller than the degree of g. So degree of m smaller than degree of g. Okay, so you can write it as a product in this manner. Then the same is true of f, because, for example, look at this guy here. This is a polynomial whose degree is strictly smaller than the degree of g. This is a polynomial whose degree is smaller than the degree of g, but the degree of f and the degree of g are the same. Okay, so degree g is the same as degree of f, right? In fact, both degrees are equal to p in this case. Okay, so this gives me a way of rewriting my So this gives us a way of rewriting f as a product of two polynomials again whose degrees are strictly smaller than f. Okay, in other words, if g is reducible, then f is reducible. And sort of you can work the same argument with the roles of f and g reversed. Okay, good. So that just shows that if f is reducible, then g is reducible and vice versa. So let's just prove that g is reducible. Okay, so claim g is reducible. So proving it, essentially we are saying that if you recall, g is just nothing but f with the value a equals 1. So what we are saying is if you prove it for a equals 1, you prove it for all values of all non-zero values of a. Okay, claims that g of x is irreducible. So it's x to the p minus x plus 1 is irreducible. Okay, so observe the following, that definitely this has no roots in the base field fp. So observe g of alpha is definitely not 0 for all alpha in the base field, because in fact if I compute g of alpha for any element of the base field, it's alpha to the p minus alpha plus 1, but we know that this is 0, so this is actually 1. Okay, so now let's prove it's reducible. Suppose g can be written as a product. Let's say m1x, m2x. I decompose it into a bunch of reducible factors mk of x. Each mi is reducible. Each mi belongs to fp of x. And what more do I know about each mi? I also know that the degree of mi is strictly smaller than degree of g. Okay, now let's do the following. Let's take the first polynomial m1 of x, and that's some irreducible polynomial. So it has a root in some extension of fp. Okay, so let beta be a root of the first polynomial m1 of x in some extension of f. So recall, this is one of the things that you learnt about symbolic adjunction, which is that given any polynomial, a non-constant polynomial, you can always construct some extension, some finite extension in fact of the base field in which that polynomial has a root. Okay, so let's take that extension. So let's consider fp beta. So I take that extension in which there is a root beta, and I consider the field fp beta over fp. Okay, so what's the degree of this extension? Well, the degree of this extension, so let's call the degree as d. So let d denote the degree of this extension. What do we know about d? D is just the degree of m1, right? m1 is the reducible polynomial. So the degree of m1 is definitely less than the degree of g. That was the starting assumption, which is p. Okay, so degree of m1 is smaller than p. That's what we know. D is smaller than p. Okay, well, that's one thing we know about d. Another thing we know about d is that, remember, beta is not an fp. So this is fact 1, is that d is less than p. Fact 2 is that d is at least 1. Okay, so I claim, in fact, I can say more, d can't equal 1. Okay, why is that? That's because d can't equal 1, since if d is 1, that will mean that beta belongs to the base field, right? But we have already seen that g has no roots in the base field. We have already shown that g beta is 1 definitely for any root beta of g. Okay, so what this means is that this is an extension of degree equal to d, which is a number strictly between 1 and p. Okay, what does that mean? Well, recall from your construction of finite fields, you have learned that if I have a finite field fp and I have a degree d extension, a finite extension, what does that mean? It just means that the field on top, thus fp of beta, it's a field whose cardinality, I mean as a vector space over the base field, it's of dimension d. So the cardinality of the field on top is just p power d, right? And you know that finite fields of a given cardinality are unique. So this is just the finite field of cardinality p power d. Okay, thus what does that mean? F p of beta is just the finite field of cardinality p power d, which means in particular that if you take any element from this field, okay, which means that if I take gamma for all gamma in this field, if I raise gamma to the power p power d, right, the cardinality of the field, I am supposed to get back gamma, right? This is the property that these finite fields have. Okay, in particular this is true if gamma equals beta. Okay, so let me now put gamma equals beta, because beta in particular is an element here. So I conclude that beta satisfies the following equation: beta power p power d is beta. So I get one equation that beta satisfies. But we already knew something about beta, right? What do we know? We already know the following, that beta was a root of g, right? Beta was in fact a root of m1, which was one of the reducible factors of g. So this means in particular that beta power p minus beta plus 1 is 0. Okay, so here's the second equation that beta satisfies. Now our claim is that these two equations can't be simultaneously satisfied for d, a number strictly between 1 and p. Okay, so these can't both hold. Okay, if d is a number between 1 and p. Okay, why is that? Let's prove this. So, you know, probably many different ways of going about the proof, but let me start with the second equation here. So I know that beta power p, I'll rewrite it as beta power p is beta minus 1. Now from this I can compute what is beta power p square. Okay, so I will just take beta power p square is nothing but beta power p the whole power p. So that is beta minus 1 the whole power p. Now, well, what's that? That's beta plus minus 1 the whole power p, and you've seen this computation many times. This is just beta power p plus minus 1 power p, because all these are taking place over a field of characteristic p, right? All the intermediate terms that you get in the binomial theorem are all divisible by p, so they all go away. So beta to the p square is just beta to the p plus minus 1 to the p. Well, what's that? So this is just beta to the p. So beta to the p I already know is beta minus 1. So this is just beta minus 1. And minus 1 to the p, well, for now if p is an odd prime, so maybe we should just assume, let's just make that assumption. Suppose p is an odd prime. I mean, you can just do it similarly for p equals 2. So let me just say case 1. P is an odd prime. Then this is again a minus 1. Okay, so this is beta minus 2. Now you can already see how this is going to go. If I compute the next power of beta to the p cubed is just beta to the p square the whole to the p. That's now beta minus 2 the whole to the p. And by the same token, this is going to be beta to the p minus 2 to the p. But 2 to the p is just 2. Okay, recall this is because 2 belongs to the base field, right? 2 is in fp. And therefore, when you raise it to the power p, you just get back itself, and so on. Okay, so what does that mean? Beta to the p on the other hand is beta minus 1. So this is beta minus 3. Okay, so in general, well, or let's do it d times, this will just give me beta minus d. Okay, so I've just repeatedly, I've iterated my second equation and concluded that beta to the p to the d is beta minus d. On the other hand, the first equation tells me, okay, sorry, I'm here, but we also know the first equation which says that beta power p power d is beta. Okay, now how can these two equations be true? Well, this means automatically that d is 0, but observe that can't happen. Why not? Well, because d is a number between 1 and p, right? So since d is strictly smaller than p, it can't happen that d is 0 in this field. Okay, so d is 0 is a contradiction. See, if D is P, then it's okay. If D equals P, then of course it means that P is just 0 in a finite field of cardinality P, right, or any characteristic P field. Okay, so that completes the proof.